Hello everyone, welcome to this video. In this video we will talk about the galvanic cell, and we will proceed with the material of electrochemistry, and we'll talk about the galvanic cell. So as a brief introduction, um, as we've mentioned before in the previous videos, we talked about the oxidation and we talked about the reduction half reaction. They are both half reactions, oxidation half reactions and reduction half reactions, because they together they form the redox reaction. And as I've mentioned before, that the oxidation half reaction and the reduction half reaction occurs simultaneously at the same time. And we talked about the redox couples, how we write the redox couple, and then we were able to place elements and redox couples in the electrochemical axes to know which elements has more strong oxidizing power than others, and which elements have stronger reducing powers. Well, if you want to understand the process here, the oxidation reduction reaction is simply the transfer of electron from one losing electrons, which is the element that undergoes oxidation, to one gaining these two electrons, which the one which undergoes reduction. And we said that the oxidation, the one that undergoes oxidation is the reducing agent, and the one undergoes reduction is the oxidizing agent. You can refer to previous videos to know why we call the one undergoes oxidation the reducing agent, and why we call the element undergoes reduction the oxidizing agent. You can go back to the previous videos to know that. Okay, so what's so interesting in this kind of reaction, the transfer of electrons? Well, actually we're interested in studying these kind of reactions because through the transfer of electrons we can design something called galvanic cell. Galvanic cell is we can find galvanic cell in batteries, and we usually use galvanic cell to make current. We usually use galvanic cell to make potential difference. We'll talk about this. So we're changing a chemical energy to electric energy, and mainly we use electric energy in our daily life. Like, we charge our laptops, our iPads, our phones, we turn on televisions using electricity. And that's why oxidation reduction reaction is so interesting, because we're changing the chemical energy. We're starting from a chemical reaction and we're ending up with current and electric energy. We will talk about it. So the main objective of this video is to define and to construct the electrochemical cell, or the galvanic cell. And we will talk about the salt bridge, what is its role inside the cell, and we will write the salutation. So each cell has its own way to express the main compartments inside the cell. Okay, and we write it as a salutation. So let's start here with this picture of the galvanic cell. Actually, this is the galvanic cell. As you can see, it's divided into two compartments. We call these two compartments. We call this the anode half cell. This is the anode half cell, and this is the cathode half cell. Each beaker with this strip inside it, we call it a half cell. As you can see here, this salt bridge. This is the salt bridge. The salt bridge is it contains jelly-like material that has minerals inside it. It's electrolytic, means it conducts electricity. In this case, we have NaCl inside it. We can put we can have potassium nitrate. We can have many other minerals inside it. That's just jelly-like, so that the material here, the chemical here doesn't drop into the beaker. It's a jelly-like material. We'll talk about its role. It drops when there is distortion in the electron neutrality of the beaker. We'll talk about the salt bridge. Now I'm concerned about the structure of the galvanic cell. So we have a zinc strip dipped in zinc nitrate solution. Again, zinc strip as you can see, dipped in zinc nitrate solution. And then this is the anode half cell. We will talk about why it's called anode. Here we have in the cathode half cell, we have copper dipped inside copper nitrate solution. So in other words, the zinc strip is dipped in Zn2 plus, and O3 minus is a spectator, and I'm not really concerned about NO3 minus. And we have copper strip dipped in Cu2 plus, okay, solution, or CuNO3 2 minus, copper nitrate, okay. So the zinc strip and the Cu strip are connected via connecting wires. The Cu strip, the zinc strip, and the copper strip are connected through connecting wires, and the solutions are connected via the salt bridge. As you can see, this is the salt bridge connecting the solution together, okay. And when we have this setup, the salt bridge connecting the two solutions together, we have the anode half cell, the cathode half cell. Cu is dipped in Cu2 plus solution, and Zn is dipped in Zn2 plus, and the Zn strip are connected to Cu through connecting wires. We have the voltmeter changes to give us 1.1, shows 1.1 volt. And we have some observations. Let's talk about the observations. So the ammeter indicates the current flow of few milliamperes from the copper strip to the zinc strip. So here, let me just put it. So the current is moving from Cu strip to the zinc strip. This is the current. Okay. As well as the voltmeter indicates a value of equal to 1.1 volts. Now here's so interesting. The color of sulfate solution fades. The color of copper sulfate solution fades. As we noticed that the copper sulfate solution has a blue color. This is blue. And the blue color of the copper sulfate starts to fade. This means that we don't have any more Cu2 plus. The Cu2 plus ions are decreasing. Okay, we'll talk about it. So the mass of zinc strip decreased and the mass of copper strip increased. Before talking about the zinc strip and the copper strip, let's talk about what's going on in this setup in the galvanic cell. So actually we have the transfer of electrons. It's an oxidation reduction reaction, and we have a transfer of electrons. The electrons are being transferred from zinc to copper. So Zn undergoes oxidation. Zn undergoes oxidation to become Zn2 plus 2 electrons. It undergoes oxidation. And here we have the Cu is receiving the electrons from the Zn, where Cu2 plus undergoes reduction, so it becomes Cu. This is undergoes reduction. Now I want you to know that the sense of the current is always the opposite of the electron flow. So if the current flows from Cu to Zn, then the electrons will flow from Zn to Cu. Okay? The transfer of electron does not take place directly between the reactants in here, as we talked before in previous examples. The transfer of electron takes place between the zinc anode and the Cu2 plus. So zinc anode undergoes oxidation. The transfer here is going through the connecting wire. We'll talk about mainly what's going on. Now I want to understand why, I want to explain why Zn is decreasing in mass. Zn strip is becoming, like you see, this strip is becoming decreased in mass. Well, because Zn is losing 2 electrons to become Zn2 plus. That's why, as you can see here, this strip is losing 2 electrons and it's dropped into the solution. So here it's losing 2 electrons, becoming Zn2 plus and being dropped into the solution. So here the Zn, the concentration of the Zn2 plus here is increasing. We will talk about what's the solution of that. Okay, so Zn here is losing electrons to become Zn2 plus. That's why we don't have any more Zn. The Zn is decreasing in mass. Here, in this case, the Cu2 plus is receiving 2 electrons. That's why the Cu2 plus is becoming Cu, and that's why the Cu increases in mass. You got the you know how we explain this? The why Zn decrease in mass and why Cu cathode increase in mass? Because here we have the Zn is becoming Zn2 plus, and here Cu2 plus is becoming Cu, and that's why the blue color starts to fade, because we don't have any more Cu2 plus. Cu2 plus actually is decreasing. The concentration of Cu2 plus is decreasing because it's becoming Cu. Okay, so again we'll try to explain what's going on. We have an oxidation half reaction. Who is undergoing oxidation? It's Zn. Zn is undergoing oxidation. It becomes Zn2 plus 2 electrons. Now we have a reduction half reaction as well. Okay, we have Cu2 plus is gaining 2 electrons. It's becoming Cu, and that's why the mass of copper strip increased and the mass of Zn strip decreased. The copper sulfate solution starts to fade, and here we have the transfer of electron. The transfer of electrons is going through the connecting wire. The transfer of electrons is going through the connecting wire. So the copper, I want just to mention one more thing before I forgot. Why we call this anode and why we call this cathode? Well, actually, the electrode that where oxidation occurs, where oxidation takes place, we call it anode. The electrode where reduction takes place, we call it cathode. And here we need to mention that this is a negative terminal. It holds a negative terminal, and this holds a positive terminal. Again, the electrode where the oxidation takes place is called anode, and the electrode where the copper takes place, the electrode where reduction takes place is called cathode. We're good? So we can produce actually any electrochemical cell using two metals as long as the reaction is spontaneous. How do we know that the reaction is spontaneous? By referring to that the element which holds the most oxidizing power should react with the one that holds the most reducing power, or the gamma rule. By referring to the electrochemical axis, if you still remember the gamma rule, this is going up is more oxidizing power increases, oxidizing power increases, and going down reducing power increases, and the two should react, the one that holds more oxidizing power to the one that holds more reducing power. This is how we know that the reaction is spontaneous. We can form the galvanic cell. It's simply we need to dip the Zn metal in Zn2 plus solution, and we need to dip Cu metal in Cu2 plus solution. This is Daniel's cell. It's a subcategory of the galvanic cell. We call this cell as Daniel's cell. The Daniel's cell is exclusive for this kind of metals, for Zn and Cu, but we can form other cells. Okay, we just need two metals, and we need to form the spontaneous reaction, and we will have the transfer of electrons from the anode to the cathode, and the current will flow from the cathode to the anode. Okay, so a galvanic cell can be constructed by using two different metals, each being dipped in an electrolytic solution which contains its ions Mn+. Here we have in the case of Daniel's cell, we have the Zn dipped in Zn2 plus, Cu dipped in Cu2 plus. Okay, the galvanic cell generates electric current by the chemical reaction. It's a purely chemical reaction. We're having an oxidation reduction reactions where electrons are being transferred from the anode to the cathode. It's a purely chemical reaction and we are generating from this chemical reaction a electric current, the overall reaction which takes place in a cell is spontaneous reaction between the redox couples involved. It should be spontaneous. So that we will have a reaction and then we have electrons moving through the connecting wire, and thus we have the current being and then we have current. Okay, so the cathode is electrode where reduction takes place or where reduction reaction occurs. The anode is the electrode where oxidation reaction occurs. In this case, in the Daniell cell, the reduction takes place in the copper strip and oxidation takes place in the Zn strip. Okay, so as we've mentioned that the copper holds the positive terminal of the cell and the zinc strip holds the negative terminal of the cell. The electrons in this case travel in the opposite side sense of the current flow from the zinc strip to the copper strip, and the electrons which travel in the external circuit are a result of a oxidation reduction reaction. It's a result resulted from a chemical reaction that invoked current, and this reaction taking place between the two compartments or the two half cells. Now the overall redox reaction, if we just add the oxidation half reaction with the reduction half reaction, we get this overall redox reaction. It's Zn plus Cu2 plus in a Cu2 plus in the aqueous form, giving us Zn2 plus aqueous plus Cu as a solid. Hope that the galvanic cell is clear. Now this cell, the Zn and the Cu, we call it Daniell cell. But the galvanic cell is a more general term for all cells that holds different metals. Okay. Now let's go to the role of the salt bridge. Well, we have two roles of the salt bridge. The salt bridge ensures the flow of electric current between the two compartments of the cell. So here we don't want to make the cell in a closed circuit. We need electricity to flow, and because we need electric current to flow inside the cell, we need to close the circuit. So how we close the circuit? We dip this electrolytic solution, as I've mentioned, it conducts electricity. We dipped it inside the two solutions. So as you can see, it's closed circuit now. Here we have the electrons being transferred, moving to the copper. Copper is being reduced, and we will talk about what's going on here inside the solution when copper is being reduced. Okay, so because we're having, this is an oxidation reduction reaction as the previous reactions we've discussed before, but the only difference here is that we are trying to control the electron flow to be outside the compartment of the beakers. We're trying to make the electron to flow inside the wires, and the electron transfer is not directly conducted between, or it's not directly, the electrons do not transfer directly between the reactants. They transfer through the electric wires. Okay, so electron goes through the wires, and because of that, we don't want to make the circuit closed. Okay, we don't want to make the circuit open. We need to make it closed, and because of that, we have the salt bridge. This is the first role of the salt bridge. Now the second role is to assure electron neutrality. Now here I need you to focus a little bit. What do we mean by to assure electron neutrality of the compartment? Now here, as I've mentioned, we have the Zn is becoming Zn2 plus 2 electrons. It's undergoing oxidation, so the Zn strip is decreasing, and here the Zn is giving Zn2 plus to the anode compartment, to this half cell. The Zn is giving Zn2 plus to this half cell, to the solution in this half cell. Now, as you notice that we started with zinc I don't remember if we started with zinc nitrate or sulfate. Let me check. Okay, so we started with zinc nitrate. Okay, it gives us Zn2 plus 2 NO3 minus. As you can see, this is concerning the charges. This is extremely neutral. We have 2 plus here, and here we have 2 minuses. So the charge is equals to 0. It's in neutral. Now, here we have the zinc NO3 2 minus inside the solution, which is neutral. But whenever we're adding Zn2 plus, we have a newcomer. You have that Zn2 plus coming from the Zn, because Zn is being oxidized. It's losing electrons to give Zn2 plus 2 electrons. So we have Zn coming from the Zn strip. This will deform the electron neutrality of the solution. The solution is now more neutral. Okay, because here the Zn2 plus is increasing. Zn2 plus is increasing. What's the solution for that? Well, the role of the salt bridge is to let NO3 minus migrates. It contains, as I've mentioned, that the salt bridge contains salts. In this case, we have potassium nitrate. It lets the NO3 minus to migrate to the solution so that it ensures electron neutrality. So we have the Zn2 plus increases. The solution is becoming more positive. The salt bridge will allows the migration, allows as a weak term. I believe that the nitrate ions will migrate. The nitrate ions will migrate from the salt bridge to the solution, and that's why it will reform the electron neutrality of the solution here. And this is concerning this the anode compartment. Let's talk about the cathode compartment. Now the cathode compartment, we have Cu2 plus is being reduced. It undergoes reduction to BCu. As you can see, we have here, we started our reaction with Cu NO3 2 minus, as well as we have Cu2 plus 2 NO3 minus, right? Now Cu2 plus, we're reducing Cu, so we're losing Cu to become we're losing Cu2 plus, we're reducing Cu2 plus, so we're losing Cu2 plus, it's becoming Cu. Cu2 plus is becoming Cu. This means that the concentration of Cu2 plus is decreasing relative to the concentration of NO3 minus. The NO3 minus remains stable. We're not consuming NO3 minus, we're consuming here Cu2 plus. So the Cu2 plus decreases in this case. Then we need because the Cu2 plus is decreasing, this solution is becoming negatively charged, because NO3 minus now is more than the Cu2 plus, because we're using the Cu2 plus in the reduction reaction. So the solution is becoming negatively charged. So it's not neutral anymore. So this is the role of the salt bridge. K plus will migrate through the salt bridge to ensure the electron neutrality. K plus will migrate in the salt bridge to ensure the electron neutrality inside the solution. Okay? When K plus, now we have here a positive charge coming, so we have the solution will reform to be neutral as it was. That's how we mean that the salt bridge, as well the electron neutrality, that how the salt bridge ensures the electron neutrality of the two compartments. It adds NO3 minus to the anode compartment and K plus to the cathode compartment. Now here the anode compartment, it's becoming positively charged because of the Zn2 plus ions being newcomers, the Zn2 plus newcomers being, because of the Zn is being oxidized. So here we need a negatively charged ions so that it becomes more neutral. So here the NO3 minus migrate to make the solution neutral again, and here we have in this solution we have it's becoming negative because we're using the Cu2 plus in the reduction reaction, so that the NO3 minus increases relative to the Cu2 plus, and K plus will take its place, will take the Cu2 plus place to ensure the electro neutrality. Okay, hope it's clear. If you have any questions, please let me know. We will go to the last idea in this video, which is the cell notation. Now the cell notation, as it's a way in order to name cells, actually, to name galvanic cells. How we can name the galvanic cell? We need to know, it's really easy. In this case, we have, in the case of Daniel's cell, we have Zn2 plus dipped in, Zn dipped in Zn2 plus. We write the Zn2 plus Cu2 plus Cu. Now we're gonna ask how I wrote this. So I started with the negative terminal. So start with the negative terminal. Our negative terminal in our case is Zn. And the negative terminal is in the left. The positive terminal is shown on the right. This is the positive terminal, or the cathode is copper. Okay? Here we have the negative terminal is Zn. Now I have one line, this line, the separation between the electrode M and Mn plus ions indicated by a vertical line which represents the phase boundary. I separate between the ions and the metal through this line. Okay? And the salt bridge is represented by two dotted vertical lines which separates the two half cells. So the separation between the two half cells is indicated through the salt bridge, which is two dotted line, or I can put them like two vertical lines. Okay, so this is the salt bridge, and this is how the two half cells separated. Okay, now we put the metal usually on the extremities. That's why I put Cu at the end and the extremity, and the Zn on the end, and we put in the middle, we put the ions. Okay, and again, how we separate the metal from the ion? One line. Cu is being separated from Cu2 plus by one line. Zn is being separated from Zn2 plus one line. How to separate the two half cells? Two lines to indicate the presence of the salt bridge. Two lines, two dotted lines, vertical lines. Now, and I start with the anode, and I end up with the cathode. I start from the left, anode, to the right, cathode. Okay? Now there is a misconception. Students tend to make some mistakes. Students could write Zn, Zn2 plus, okay, Cu, Cu2 plus. Again, this is wrong. This is wrong because I need to put the metals on the extremities. As you can see, the metals are on the extremities. And some could do another mistake, which is they could find it, they could merge things up, and things could confuse them to think about the redox couple. So they can write like Zn2 plus, Zn, Cu2 plus, Cu. Well, also this is wrong because here it's another way to represent cells. I know that to write redox couples, the two redox couples involved here is Zn2 plus, Zn, Cu2 plus, Cu. But in representing the galvanic cell, in writing the cell notation of the galvanic cell, here in our case is Daniel's cell, we start with Zn2 plus, the metal should be in the extremity, one line between the metal and the ion, and the ions are inside, two lines to separate the two half cells, or to point for the salt bridge. Now the last idea, as we've mentioned, before that, we have here the chemical energy is being transformed into electric energy. In the galvanic cells, okay, chemical energy is being transformed into electric energy. We have in the previous videos we've conducted several experiments concerning the oxidation reduction reactions, and where electrons are being transferred from one reactant into another. Now, this is the same process. We have an oxidation reduction reaction, but the transfer of electrons is outside the compartment, okay? Or let me say that we are trying to control the electron flow so that it passes through the connecting wires, okay? The electron transfer between the reactants, it's outside the beaker, or outside the half cells, okay? So this is the half cell, this is the Zn half cell, and this is the copper half cell. Now the electron transfer is outside. As you've mentioned, the electrons are moving through the connecting wires outside the half cell, but it remains an oxidation reduction reaction, okay? So that's it for today. Hope you enjoyed the video, and we will catch up later. Thank you for your time.